Let's face reality. The future of fossil fuels is doomed. Growing concern over the existential threat posed by climate change is motivating a large-scale transition from greenhouse gas-producing fossil fuels to clean, renewable energy. But what is renewable energy really? Renewable energy refers to energy harvested from sources that can't be depleted, such as the sun or the wind. Contrast this with fossil fuels. We're running out of oil, but we can't run out of sunshine. One problem with renewable energy is that it's intermittent. The sun isn't always shining, and the wind isn't always blowing. So how can we expect to turn the lights on at night? Are renewables a feasible solution? The answer is yes, with a few adjustments to our power grid. Right now, the US burns fossil fuels on demand. This means that the grid does not store energy. So if we can't use up all the energy we harness immediately, we lose it. And this is a problem if we're switching to intermittent renewables. If we can find a way to store this unused energy, we can deploy it later when we actually need it. When we have to turn the lights on at night, we can make use of the solar energy we've stored away during the day. This gets us to battery-assisted load balancing. The batteries you'd use here aren't the ones you're probably thinking of. While the small lithium-ion batteries in your smartphone can hold a lot of energy, lithium is scarce, making these batteries very expensive at grid scales. They're also prone to ignition if not handled carefully. So what's the alternative? Enter Redox flow batteries. These are suited for grid energy storage due to their safer chemistry and greater cycle life. Before we get into the specifics of Redox flow batteries, what even is a battery anyway? A battery is a device that uses magic, otherwise known as chemical reactions, to both store and release energy. Similar to how a ball on a hill has stored energy, the chemicals involved in these reactions can also store energy. Most batteries are made up of two solid electrodes, connected by an external circuit with a chemical called an electrolyte between them. At one of these electrodes, called the anode, chemical species give up electrons in a chemical reaction, which also creates charged species, or ions. These electrons can now flow outside from the anode in an external circuit, and this flow gives us energy. But we can't let these electrons roam free forever. They return to the battery at the other electrode, called the cathode, where they get recaptured in a chemical reaction by ions that traveled through the electrolyte from the anode. The higher the hill, or energy difference between the anode and the cathode, the more energy can be released when the reactions happen and the species react, or when the ball falls down the hill. We've only described what happens when we discharge a battery to get energy, but when we want to charge it, we just push the ball back up the hill by reversing all the reactions and electron flow. In an ideal world, we'd be able to charge and discharge batteries as many times as we'd like, but you probably know that your smartphone batteries don't last forever. The more you charge and discharge most batteries, the shorter the battery life gets. This happens because apart from the reactions at the electrodes that we want, the ions can get involved in other unwanted reactions that interfere with the performance of the battery. We can put a membrane between the electrodes to only allow the ions we want to pass through while rejecting others, but these membranes degrade over time, causing even more seepage of ions. This ends up decreasing the battery performance by making your hypothetical hill smaller. It's a problem that plagues most battery technologies, but what if there were a way around that? Instead of solid electrodes, redox flow batteries pump liquid electrodes from holding tanks into the battery cell, where the magic happens. Many flow batteries use vanadium as their anode and cathode. Vanadium is ideal because it's versatile. It can release a number of different electrons and exist as ions in a different number of charged states, such as V2+, V3+, V4+, and V5+. During charging, the renewable energy pushes the hypothetical energy ball uphill, ready for discharging when needed. Introducing energy causes V4+ to lose an electron and create V5+ at the anode. This electron goes through the external circuit and is captured by V3+ to make V2+ at the cathode. The V5+ and V2+ that were created are pumped into holding tanks. When we need energy and discharge the system, we reverse all the reactions to release energy into the grid. While vanadium's versatility is great, vanadium batteries need more space than lithium-ion batteries to hold the same amount of energy. This makes these storage plants pretty big, but since they're stationary, this really isn't an issue. And if we want to store more energy in each battery, we can simply use larger tanks. So what's so special about these batteries? For starters, the electrolytes used in these batteries are non-flammable and much safer than their modern-day counterparts. Also, when used for load balancing, the flow battery's ability to turn on and off rapidly allows for uninterrupted power. But the most exciting part about these batteries is that they can last for a long time. Swapping a worn-out membrane without replacing the vanadium solution is fairly easy and restores the performance of the battery. This would allow you to keep your grid storage running with few interruptions and save money at the same time. We took you on a bit of a wild ride here, so let's recap. Earlier, we asked whether the transition to renewable energy was feasible. Now, from a technical perspective, redox flow batteries will be key in overcoming the intermittency associated with renewable energy by providing energy storage solutions, ensuring renewables can supply energy all day and all night long. From an economic point of view, on the other hand, major energy producers are diverting investments from fossil fuels to renewable energy because renewables have been providing an extremely high rate of return as of late, owing to federal and state incentives on investment. For instance, in the US, renewables yielded a 200.3% return on investments over the last 5-year period, as opposed to a 97.2% return for fossil fuels. Renewable energy stocks are also very stable as opposed to oil and gas stocks, with oil prices literally hitting sub-zero amidst the pandemic, as we all witnessed. So, can we transition to renewables from fossil fuels while ensuring the lights never go out? The answer is yes, yes, and yes. So get ready for a world powered by green, clean energy.